Now you can see we're still solving radical equations, but now there are two radicals. And it got cut off a little bit here, but we never want to have two radicals on the same side of the equal sign. That will help us solve these a little bit better. So the first thing we're going to do is add this root 2x to both sides. That'll give us the square root of x plus 9 equals 3 plus root 2x. Now, in order to get rid of the square root in the previous examples, we were squaring both sides, and that will work this time. If we square this side, we're just left with x plus 9. But on this side, when we square this binomial, that means two terms, we would actually want to think of it as writing it out 3 plus root 2x times 3 plus root 2x. So the left side's not going to change, but when I multiply out these two terms on the right, I'll have 3 times 3 makes my 9. And 3 times root 2x, we're just going to write that as 3 root 2x. Then I have another one here, a 3 times root 2x, so I'll write that again. And root 2x times root 2x, you know it's positive. That will be root 4x squared. Now some of you might see that is going to reduce, but we'll do that here in a second. So let's combine some like terms here. We've got our 9. We have 3 root 2x's and another 3 root 2x's, so we have 6 root 2x's. And the square root of 4 will be 2. And the square root of x squared is x, so that one comes out of its radical. Now we're going to get everything on the same side, so I'm going to go ahead and subtract the x here and the 9 from both sides. Subtract 9 and subtract x. That'll give me 0 equals 9 minus 9 is 0. I have the 6 root 2x, and 2x take away x makes x. Now this isn't a quadratic, so I don't want to use the quadratic formula or solve it. So I'll go ahead and move one of them to the other side. So I'm going to subtract this x from both sides, and that gives me negative x equals 6 square root of 2x. Here we are again with another radical sign, and we want to get rid of it. So again, to get rid of the square root, we're going to square this. We get to square twice now in order to solve for our x. So a negative x times a negative x is a positive x squared. When I square the 6, I get 36. And when you square a square root, remember these are going to cancel each other, so I'll just have times 2x. That means I'll have x squared equals 72x. Now I can go ahead and bring the 72x to the other side by subtracting 72x here, and from this side I'll have x squared minus 72x equals 0. And now we finally go back to that factoring. Lots of steps here. Take out an x from both these terms, leaves me with x minus 72. And I will know from this x that 0 is one of the solutions, and from this x, 72 is a solution. We always need to check for those extraneous solutions. That is, we need to plug them back into the original radical equation. So with some quick substitution here, I plugged in 0 to the original radical equation, and I get the square root of 9, which is 3. It does equal 3. So 0 is definitely a good solution. When I get the 72 here, square root of 81 makes 9, minus the square root of 144 is 12. That's going to be negative 3. It does not equal 3. So our 72 is extraneous. Now, we know x0 is our solution. Look right here on the graph. You're saying after all this time, we could have just used our radical equation that was graphed on the left. That's what's graphed here in orange. And equaling the line 3, it does indeed cross at x equals 0. It would be acceptable if you wanted to check for extraneous solutions by just plugging these equations into Desmos. You could type this all on Desmos, or at least the left side, and see if it makes 3 to know if it's going to be extraneous or not. Now, as you noted, that first example 5 was definitely a long problem. These will be the same, but the process will be very similar. You could follow step by step with these changed numbers, but you can note also that I did graph the radical equation for part A in blue and the negative 2 in red. We know the answer should be x equals 12. you will get another solution where you'll have to check if it's extraneous. And of course it's going to be because we only know our one solution is 12 here. But check the answer key from your packet to be able to see how to do these two problems for the triad. You can double check if your teacher will be doing example 6. But just a quick application problem. This one has the body surface area, so the outer covering of your skin. That's determined by this formula here. And h is your height in centimeters and m is your mass in kilograms. So they're wanting to calculate how much medicine you would need, who your body surface area is less than 1.9. Now you notice this less than idea. We know the patient is 160 centimeters tall, so that's my H, and they want to know what is the mass. We don't know the M. So they want the body mass, the body surface area, to be 1.9. So if I fill in the numbers that go with this equation in their correct spot, my H is 160, my M I don't know, and my 3600 is in my denominator. Notice we want the BSA to be less than 1.9. So we note that it has to be less than the 1.9, so we're going to actually use one of our inequality signs. We want this body mass index to be less than 1.9. So we'll say this is our gator because we want this answer to total less than a 1.9 body mass. So if we're going to solve this, we would we have to just follow those same protocols. We're going to square both sides first to get rid of that square root. So 1.9 squared comes out to 3.61. And then we can just treat this gator or inequality symbol like an equal sign. If I square a square root, I'm left with just what's underneath. So 160m over 3600. Now I'll multiply by 3600 on both sides. And that gives me 12,996 is greater than 160m. So this one's actually much easier to solve, even though it was part of a story problem. So don't let that fool you. I'm dividing by 160 now here, and that will give me my m, or their mass, needs to be less than 81.225 kilograms. So notice how we can use these radical equations in a real world situation to solve for a variable if we know at least one of the other variables.